Hello everyone, my name is Allie and I am the SI instructor for Chem 140 at Cal State Long Beach. If you are not in Chem 140, I don't recommend watching this video because the rules that they learn are slightly modified than real ochem rules and this may confuse you. But if you are in Chem 140, I do recommend watching this because it's hard to find resources that fit what you're learning in particular in your class. So today we're going to talk about carboxylic acids. They're so cool. They're the coolest. Do you know why they're so cool? I'll show you why they're so cool. Because they have a formula like this. The condensed formula for this is Cu. So if I say Cu, I mean carboxylic acid. And just to kind of like clear this muddy water right now, you might be thinking, dude, I remember from Gen Chem, OH means base. In this case, that's not the case, because this hydrogen is very what we call acidic. It's going to pop off easier because the oxygen is pulling electrons towards it. The oxygen is also pulling electrons toward it from the carbon. This oxygen is pulling electrons toward it from the carbon. So there's a lot of pulling. And all the pulling means the hydrogen can be easily plucked off and become an H+ and go off and be someone else's problem. So that's why this is an acid and not a base. Okay, so how we name these guys, we'll start off with this example. The IUPAC name for this is propanoic acid. A common name for this is going to be propionic acid. You add the oic acid ending. For this, you're adding the IC ending. And just as a refresher, there are 4 different prefixes that we are going to see for carbons 1 through 4. 1 prefix for each. And these are common prefixes. They're not the IUPAC ones. So for 1 carbon, we say form. For 2 carbons is acid. For 3 is propion. And for 4 carbons is butyr. That's why this is propionic acid. Now, what if we add a substituent at a particular location? What if I add a methyl group here? And what if I add a chloro group here at the end? Well, these have particular names for locations and common nomenclature. So why don't we go ahead and name this IUPAC first? Why don't you go ahead and try this on your own, pause the video and attempt this, and then we'll go over it. Now that you've attempted this on your own, you see that it's still going to be propionic acid. That's still going to be the ending. Oh, I'm sorry. For IUPAC, it's not propion, it's propanoic. I was getting ahead of myself there. Propanoic acid. And the carbonyl, the carbon from the Cu, that's always carbon number 1, no matter what. No matter if you have, like, even though the chloro's over here, maybe like it's alphabetically prioritized. No, this is always carbon number 1, 2, and 3. So what we're going to say is we're going to say 3 chloro, 2 methyl. Propanoic acid. I like saying propionic, I don't know why. Propanoic acid. 3 chloro, 2 methyl, propanoic acid. And the reason why we arrange these, of course, is because chlorine comes before methyl in the alphabet. C, it comes before N in the alphabet, therefore this is named first, even though the number is larger. Now, for common names, we're going to use propionic acid, which I guess I've been waiting to use that or something. So, propionic acid, that's the common name because we are using the common prefix. Now, instead of numbers, we use Greek letters. The position next to the carbonyl carbon, i.e. carbon number 2, this is called the alpha position. Carbon number 3, this is the beta position, and so forth. For your purposes, you only need to know alpha, beta. Depending on what semester you're in, you might need to know gamma. Gamma would be carbon 4, if you need to know that. This semester they didn't do it. Anyway, so we have the same name now, but instead of saying 3-chloro, we're going to say beta-chloro. And yeah, you're going to do a hyphen between. Beta-chloro, alpha-methyl propanoic acid. Wait a second, there's something wrong with this one up here. What's wrong with this? There shouldn't be a hyphen there. And this is all one thing. My apologies. Propanoic acid. Cool. So, let that simmer in your head for a second, and we'll do some more naming. Let's give you another one. Let's give you, let's give you this. And let's say, let's do this. Go ahead and try naming this on your own in common nomenclature and in IUPAC. Go. Now that you've had a chance to work on this on your own, let's go over it. First we'll do the IUPAC name, and then we'll do common. So IUPAC, you have 1, 2, 3, 4 carbons in the longest continuous chain. So 4 carbons would be butanoic acid. On carbon 2, you have a hydroxy group. And on carbon 3, you have a dimethyl. So, remember, if you have mono, di, or tri, you ignore that and you just look at what kind of substituent it is. You look at the methyl portion. So H comes before methyl. So this is going to be 2-hydroxy, 3,3-dimethyl. I always run out of space. 3,3-dimethyl. Butanoic acid. And there is a space there between butanoic and acid. Cool. So now the common name, instead of butanoic acid, we're going to replace that with butyric acid. And instead of saying 2 for hydroxy, this is the alpha position. So we're going to say alpha hydroxy dash. Since they're both on the beta carbon, instead of saying 3, 3, you're going to say beta, beta. Beta, beta. Beta, common, beta. Comma, rather. And these are kind of treated as numbers. That's why you separate them by commas and you separate them with letters with dashes. Beta, beta, dimethyl butyric acid. And that's how you name that in common nomenclature. Let's go ahead and give you a bit of a trickier one. For this one, you can't do common nomenclature because it's going to be longer than 4 carbons. And beyond 4 carbons, we don't have prefixes for those in common. So we're going to not do them in common. Why don't we go ahead and ooh, what's that? That looks funny, huh? Then why don't you go ahead and name this on your own? I'll leave that up there. So now that you've had a chance to attempt this on your own, let's go over it. What's the longest chain? 1, 2, 3, 4, 5, 6, 7, 8. Let me check that. 1, 2, 3, 4, 5, 6, 7, 8. So this is going to be octanoic acid. Octanoic acid. And we have a methyl on 2. Let's go ahead and number them. So I have a bromine on 6. What is this group on 7? Is that a flag just like hanging out there? No, it's not a flag. It's a cyclo, and there are 4 carbons. 1, 2, 3, 4. So this is cyclobutyl. Okay. And then we have the dimethyl up here, but since there's a total of 3 methyl groups now, we're going to say trimethyl because in the whole structure there's a total of 3 methyl groups. So, but again, we're not going to alphabetize that. I like to put my substituents down and then alphabetize them. It just kind of helps me sometimes when I have more stuff going on. So I know I have 2,3,3 trimethyl. And I have 6 bromo, and I have 7 cyclobutyl. So I see that bromine is going to come first, and then the cyclobutyl, and then the 2,3,3 trimethyl. I think I'm going to need a little bit more space on that. So we'll say 6 bromo, 7 cyclobutyl, 2, 3, 3 trimethyl, octanoic acid. Whoa, that is a mouthful. Kind of boardful too. So I hope that made sense. Now, carboxylic acids, they do a lot of chemistry. And one of the reasons is because this group right here is extremely polarized, as I explained in the beginning. So, I'm going to go ahead and erase this name. There are a few different reactions that I want to talk about. I want to talk about neutralization, esterification, and amidation. Amidation. Okay. Let's go ahead and work with an easier carboxylic acid just so I don't have to like draw this stuff all the time. So I'll just keep working with this one for now. We'll just do butanoic acid, just to make it. So first, let's talk about neutralization, then we'll do esterification, and then we'll do amidation. So neutralization. You know from general chemistry that you take an acid plus a base, and that makes salt and water, right? That's exactly what you're doing here. This is an acid, and because of the base, such as sodium hydroxide, then you get a salt and water. But the question is, what kind of salt do you get? Let's see. So if we're making water, you're taking the OH from the base and the H from the carboxylic acid, and that's going to give you water. HOH or H2O. Same thing. And what's left over? Well, we're still going to draw what we have over here, just without the H on it. And it's going to be a negatively charged. It's going to have a negative charge now because you essentially took away an H+. So if you take away an H+, there has to be O- left over. And now the sodium's like, well, dude, my OH got stolen by this H over here, so I'm going to hang out with this guy. And you know, I'm pretty positive, and this O- is looking pretty good right now, so I'm going to hang out next to him. And so, let's go ahead and just put the common, like, the names for this guy up here. So we know that the IUPAC name is butanoic acid, and the common name is butyric acid. Now this here, this is called a carboxylic salt. It's a salt because there's a negative ion and a positive ion. And the way that you name this is you put the name of the cation in front. If you're ever naming something ionic, the cation always goes first. So you're going to say sodium. And then what you're going to do is you're going to take the name from the acid, butanoic acid. I'll do IUPAC first. And instead of the OIC, it's going to be O8. So we're going to have sodium butanoate. But the common name for this, what do you guys think? Still going to be sodium. But instead of butyric acid, you're going to drop the ic and you're going to put 8. So it's going to be sodium butyrate. And that's it. So that's how you neutralize a carboxylic acid. You just have a base. Pretty straightforward. Okay. So neutralization, we're good on that. Let's go ahead and do esterification now. Neutralization, complete. Yes. Got that. Now, esterification. What does that sound like? Well, it looks like, well, it doesn't sound like we're making esters, because we don't say ester, we say ester. But it looks like we're making an ester, and that's exactly what's happening. And you need an alcohol. The carboxylic acid plus an alcohol. I'll use propanol. For this. So for this, what's happening is, again, you're going to be making water. And the catalyst for esterification is acid, presence of acid. You get this. Okay. Actually, to make it a little bit easier on you, I'm going to draw the OH in a different way. I'm going to draw the OH over here. And the reason why is because you're making water. And what specifically happens is that the OH from the carboxylic acid and the H from the alcohol, these guys go away and they make what? Make water. H2O. So what's left? What's left after we make water? Now you have your ester. Because that guy's naked now. And you know, in fact, why don't we go ahead and draw this in red so I can just kind of show you. Yeah, so we'll do that. So now let's go ahead and draw the acid component. That's all that's left. And now it's going to bond to this oxygen because this carbon needs somebody, this oxygen needs somebody. It's a perfect match. And that's what you get. And naming esters is very similar to naming salts. So it's a little bit confusing because you might think, well, how do you know you have a salt versus an ester? And there's a very easy way to determine. So for naming esters, what you do is you take the alkyl group that came from the alcohol and you name that first. So this is a propyl group. And for esters, we are only naming common actually for esters. So we have propyl, and then you leave a space, and then you take the acid component, butanoate, well, butanoic acid, but you're turning it into butanoate. So you say propyl, butanoate. So you see it has the same ate ending that a salt did, but the difference with the salt is you're going to see a cation in front. For an ester, you're going to see an alkyl group in front. And I'll kill you if you don't remember that. Yes, that is correct. So propyl butanoate. If you want to be even more common than this, you can say propyl butyrate. So that's like two ways of saying this. But I believe this is common. I believe this is common nomenclature and not IUPAC, if I'm not mistaken. In fact, if I can have you hold on just a moment while I check my notes. Actually, that is IUPAC. This is IUPAC. Bringing in my notes here. This is IUPAC, and this one is. So there you go. And that's how you do esterification. You're creating an ester. Now, what if instead of a propyl group, we had an isopropyl group? What if it was isopropyl alcohol? How would that make things different? Well, now you need to say what carbon the oxygen's attached to, because over here the oxygen's attached on the carbon 1, and unless otherwise stated, we're going to assume so. So if the oxygen's on carbon 1 over here, we don't need to put that, but the oxygen's on what carbon number over here? It's on carbon 2 now, so now we need to specify that. So let's go over here and let's change this up a little bit. Same reactions occurring, same thing, but just the orientation is different because this is an isomer of propyl alcohol. So now you have this. So instead of saying propyl butanoate, you're going to put a 2 in front. 2-propyl butanoate. And that's because you're showing that the oxygen is attaching onto carbon number 2. And the same thing for down here for the common. You're still going to put 2-propyl butyrate. And that's how we do esterification, and that's how we name esters. So let's go ahead and do amidation. Amidation, amidation. Amidation, 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 amidation. It just reminds me of the Amadeus song, which I'm singing terribly. You're welcome. You're welcome. Okay. Oh, well, we don't have that anymore. We're doing some new stuff now. Okay. We're making an amide now. Just like esterification is making an ester, amidation is making an amide. Sorry, we'll OCD. This is when you have an acid plus a primary or secondary amine. You cannot do this with a tertiary amine. Can't be done. And I'll show you why in a second. So I'll show you with a primary amine first. Well, it can also be done with ammonia, technically, because ammonia is the simplest amine, right? What if I have this? This is ethyl methylamine in common nomenclature. There's going to be a different video on that too, soon, hopefully. And so this guy here, this is an amine, ethyl methylamine. The IUPAC name for this guy is, you take the longest alkyl chain, which is the ethyl group in this case, and that's your parent. So this is the common nomenclature. It's way easier. And for IUPAC, it's a little bit different. So you say ethylamine, and then you say N-methyl. N-methyl ethylamine. This shows that the ethyl group is attached onto the nitrogen as opposed to possibly the ethyl group. That's how you name this in IUPAC. So when you're doing amidation, you are going to make water again. OMG, we're making so much water all the time. Taking out some H2O. And what's left over? You have your carboxylic component, and you have your amine component. I'm going to draw it down here. No, I'll bring it over here. I'll bring it over here. So we have, but now it's going to be attached to the N in the amine. And you're still keeping those groups on there. And this is now an amide. Specifically, this is a di-substituted amide. I'm sorry, if I said this was a primary amine, I was totally incorrect. This is a secondary amine. I think I said primary. This is a secondary amine because you took two hydrogens and replaced them with alkyl groups. So, my bad. Sorry about that. So this is a di-substituted amide. And how we name this is, it's similar to naming esters, where you name the stuff on the N, on the other side of the N first, and then you name the acid component. So if we're going to do the IUPAC name, we're just going to tack on this IUPAC, but we're just not going to put amine at the end anymore. So the N-methyl ethyl butanamide. Instead of butanoic acid, you're saying butanamide. And the common name is very similar, except for you're going to take the common name from the amine, which is ethyl methylamine, ethyl methyl, but you're not going to put amine because that's not the functional group anymore. It's ethyl methyl, and then butyr. So instead of butyric acid, we're going to put butyramine. butyramine. Hope you can see that okay. So that's how you name amides. Yeah, not too crazy. So again, this is with a secondary amine. I apologize again for misspeaking earlier. So we have talked about how to neutralize a carboxylic acid, esterify a carboxylic acid with an alcohol, and we've talked about creating amides with a carboxylic acid and either a primary or a secondary amine. How do you think this is going to be different if we have a primary amine instead? Simple. It just looks a little bit different. Let's just replace, I just left that there. This is a primary amine, right? So if I just did this, then I would just kind of do something like, something like this, and it's the same thing, and then the name, of course, would change. Instead of ethylmethylamine, this would just be ethylamine, of course, all one word. And then there's no need for N anymore. It would just be ethylamine for the IUPAC name. So in this case, they'd be the same. And then same thing over here. You just have ethyl butanamide, or you'd have ethyl butyramide for that, for using the other amine. And if that was confusing, the joy of this is you can rewind and see what I said. So I hope that helped you with carboxylic reactions and amides and all kinds of stuff. So good luck with your studies. I'll see you guys later. Some of you in my class. Anyway, bye.